Good morning and welcome everyone to the SIGGRAPH class, Introduction to the Vulcan Computer Graphics API. My name is Mike Bailey, and for the next roughly 3 hours, I'll be your instructor. So thanks for being here. First of all, there is a website set up. It is right here. And if you go there, you'll get the very latest version of the notes. You'll get files that you might find useful. You'll get some class assignments I used here at Oregon State. Anyway, it's a good place to go. What are the goals of this class? Well, I want to give a sense of how Vulcan is different from OpenGL. And that's kind of important because I think most of us are coming at this from, hey, I'm pretty good at OpenGL. How different could Vulcan be? Well, a lot, as you'll see. We're going to talk about how to do basic drawing in Vulcan. That's what you need to know right now. And I'm going to leave you with working, documented, understandable, hopefully, sample code. First, let me introduce myself. I'm a professor in the computer science department at Oregon State. I've been doing computer graphics for over 30 years. Yikes. And I've had over 8,000 students in my university classes, and I teach a Vulcan class here at the university. So I've got a little bit of a sense of what it takes for newcomers to Vulcan to pick it up. And here's my email address, and you're welcome to send me email if that would be helpful to you. It would be helpful actually to me if you would, in the subject line, put something like SIGGRAPH Vulcan so that I can pick you out from the other classes. All right, here's what we're going to do. And if you go to the website, that full set of notes includes all of this. Now, if I did all of that, it would be probably 4 to 5 hours. And so I wasn't ever going to do all of that. And then SIGGRAPH asked us to cut it down even more because we're videoing the classes. So the grayed out ones are ones I'm not going to get to on this video, and they're not in the abridged notes. But if you go to that website, you'll see a set of notes that say full notes, and the full notes have all of that. So have at it. And then in some ways, I think you're going to find out this is a lot like, I envision a reality TV show. Of course, I'm recording this at home, and I've got the window open because it's a nice day, at least this early in the morning. And if the neighbor decides to mow the lawn, well, I'm going to excuse myself, reach around, shut the window. You may hear a dog bark. Yep, that's just how it is these days. First of all, this is a great reference. This is my favorite Vulcan reference. I'm hoping Graham Sellers updates this soon because there's a lot of stuff that's happened in Vulcan since this was written, but this is a really, really good book. And so I recommend you get this or get the version that I'm hoping comes after this. All right, so introduction to Vulcan. What is Vulcan all about? Yep, here it is. There it is. If you can zoom in on this, well, then you know everything there is to know. Yeah, this is a Wordle from the notes. Good luck. All right, so why was Vulcan created? Well, Vulcan was created for 3 reasons: performance, performance, and, well, performance. OpenGL is great. It's been around for over 20 years. Many pieces of software have been written around it, but OpenGL is really easy to use, really friendly. And as such, it's got a lot of internal checks, and it's doing some things for you, and it's kind of guessing at what you have in mind. And as such, it's incurred a lot of inefficiency over the years. Well, if you're writing simulations or games, you don't want to put up with that. That is, you really would like it to be as fast as possible. And so this is where Vulcan came from, DirectX 12, Metal. They all 3 really follow the same kind of idea that we want to be more efficient, even if we have to be more confusing. And so, yes, that's what's going on. Just as a quick aside, this is a term you may have run into, GL Next. When the Cronus group started looking into Vulkan, the effort got nicknamed somehow GL Next. That created the impression this was going to overtake and replace OpenGL, and it's not. OpenGL will be around forever and ever, I believe. But Vulkan is really where you want to go if you want to go for the performance. If you haven't learned either, I actually wouldn't recommend you start with Vulkan. I'd recommend you start with OpenGL because there's a lot of graphics programming concepts you can get there fairly easily, and go to Vulkan after that. All right, this is a block diagram of an early version of OpenGL. It's OpenGL 4.2, and it's the pipeline. And look at all the options, like all the little switches. Oh, if I'm in this mode, go here, and if I'm in this mode, go there. Well, all those little switches and all those things you could do in OpenGL, well, they have to be set. Flags have to be set, flags have to be tested. This is sort of the diagram from hell that things like Vulkan and DirectX 12 and so on were meant to replace. That is, you really want a pretty straight path through the graphics pipeline. All right, also, who's the Kronos Group? The Kronos Group is a nonprofit member-funded consortium. They do a lot of standards. Standards you've heard of, well, like Vulkan, like WebGL, like OpenGL. Here, OpenGL Embedded Systems, XR for virtual and augmented reality, and so on. They are a good group to get to know. Kronos.org is their website. There's just a lot of stuff there that if you're in computer graphics, you care about. OpenCL for compute, TF for the transfer format. Again, this is a great group and a great set of efforts to get to know. Here is, last time I went out and looked, who's in the Kronos group. And in many cases, it's round up the usual suspects, of course. The big computer companies, the big graphics companies, software companies are in the Kronos group. Universities are in the Kronos group. If you play Where's Waldo, oh, look, there's Oregon State University right there in the middle. Yeah, I joined a few years ago. It makes it a lot easier to kind of keep up with the standards efforts if you're on the inside than on the outside. Here are the companies really that have been involved in Vulkan, the subset of the Kronos group. And again, it's sort of round up the usual suspects. The graphics companies, the computer companies, the game companies, the game engine companies. You see Unity and Unreal. And this really was one of the cool things about the Vulkan effort is they made a concentrated effort to include software companies in it. Normally graphics APIs are written by hardware companies, but Vulkan had a lot of software input, so this is great. This is one of the things I think that contributes to the strength of the standard. All right, here is some of the big things you need to know. In Vulkan, more low-level information must be provided by you rather than the driver. Okay, one of the efforts, one of the maybe secret things in Vulkan was to try and simplify drivers. Well, they simplify them by putting some of the burden onto you. The screen coordinate system is Y facing down. That's not a big deal. It sounds like it is, it's not, and we'll look at how you handle that. There's not a current state, not in the OpenGL sense. You are going to create the current state. It's something called the pipeline data structure, and we will spend a bunch of time on that because that's huge. Okay, in OpenGL, we've talked about things that are deprecated, like GL begin, GL end, GL vertex 3F. They have been what I call deprecated, meaning don't use them, but we're going to keep them in the libraries anyway. In Vulkan, features such as that are what I call deprecated, meaning they are gone. Yeah, okay, there's not even a little aroma of them in the spec. Okay, so things that you've heard in OpenGL are deprecated and you're using them anyway, well, they're gone. That is, and one of the things that means is everything must be done in shaders. Okay, so in Vulkan, there is no fixed function pipeline. Everything needs to be done in shaders. And what's kind of cool, it takes a little getting used to, but it's actually a good thing, is your shader gets sort of half compiled outside of your application. And again, we'll talk about that because that's something really big we need to know about. In OpenGL, your pipeline state is a combination of whatever graphics attributes you set, the color, the transformation, and so on. Well, people discovered that changing the state one item on the fly is very expensive. So Vulkan makes you put everything in a pipeline state object. In these notes, I call it the pipeline data structure because really it is a data structure. You think, like, what's a state object? It's a struct, or really a set of structs. But again, we'll come to that. Yeah, okay, here it is. Well, again, we will come to that. This is the pipeline data structure, but if you look at it, you'll see a lot of things that you recognize, like, oh, here's viewport information, here's topology information, here's scissoring information, here's like the cull mode or the polygon mode, here's stuff that you could have set in OpenGL about using the depth buffer, here's stuff you could have set about the colors and the blending and so on. And so the things that you know about, if you're been using OpenGL, the things that you know about that you're used to using, they are still there. They're just being represented in a different way, a little more burden on you, but in exchange for that, you're going to recover some efficiency. Here is a way of programming that you're going to see a lot in Vulkan. For instance, supposing we are trying to find out what physical devices are on your system that are Vulkan capable. Well, you could have one function that says, go out and count them, bring back the count. I will now create an array of structs to hold the information, and then have a second function that says, and go out and fill this array of structs. Instead, what the Vulkan API does is it combines the two functions together. So here is one function, here is the other function, and look, they're the same function. And so the way you do this is, if you are not asking to have a struct filled, you put a null pointer in place of where the struct pointer would have been. What that says is, I'm only interested in bringing back the count. Now we use the count here to allocate that array of structs. And now on the second call, we will send in the array of structs to be filled. Get used to it. You see this all through the Vulkan API. In fact, you'll see it in OpenCL as well if you get into OpenCL, okay? So the count, yes, but the difference is null pointer if you don't want to fill anything, and pointer if you do. You're also going to see a lot of pages in these notes that look like this. Because there's so much information you have to provide, what Vulkan didn't want to do was create functions with 25 arguments. And so instead what they do is they will give you a struct. This is a type-def struct name. You fill the struct elements, and then you pass in the address of that struct into a function. Okay, so think of it as function arguments, but in fact, they're not. And in the notes and in the sample code, those structs get created and filled right before they're needed. So, oh, fill it there, use it here. And in fact, really what you'll figure out is you could create a lot of those structs at the start of your program and just they hang around and you use them when you need them. In these notes and in the sample code, we've created those structs right before they're used all the time. mostly so that you know what's going on. I hate it when I look through sample code and something's been given and now I've got to go flip through pages and pages of it looking for where that was created. Well, here you don't have to do that, but understand you probably don't want to make your code work that way. The Kronos group does have a Vulcan quick reference card. It's a PDF. We're up to Vulcan 1.2, but last I checked, there was not a 1.2 quick reference card, but there is a 1.1. You know, if you go out there and you find a 1.2, use it instead, but the 1.1 will work just fine for 99% of what you want to do. All right, here's sort of the overall structure of a Vulcan application. You've got the Vulcan application over here. You create something called an instance, and instancing, I wish they hadn't done this. Instancing means something when you're doing graphics, but here it means a set of devices with certain properties. And you can have the same devices but different properties and call that two different instances. Okay, the physical device is, well, the physical device. The physical devices are sort of aliased into logical devices, and there's queues and command buffers pointing to the queues down here. This is how it could be if you wanted it to be. In fact, for many things, it looks like this. Like there's one instance, there's one physical device you're using, one logical device. But again, Vulkan was written with all this flexibility in mind so that it can adapt to whatever you're running on. All right, here is the list of things you've got to do to get a Vulkan program running. And you're looking at this and going, oh, in these notes, and this is not an official Kronos Vulkan list. This is my list. And I've tried to break it up into very tiny discrete pieces so that if you look at a discrete piece, you look at it and you go, oh yeah, that makes sense. And then you look at the next piece and say, oh yeah, that makes sense. And so on. And then when you get all done, you go, oh, I actually have an application here and the pieces all make sense collectively as a whole. That's been the goal. So that's why there's so many, but it's not going to seem like so many when we get into it. In the sample code though, there are comments in front of each piece and they have the same numbers as you see on this page. Okay, so that's there to help you. So if you, what I oftentimes do is print this page, print this this list so that I can kind of follow the logic as I'm looking through the discrete pieces. I wanted to make a quick comment on the sample code included with these notes. And when I say included with these notes, I really mean out on this website. And I'll keep that up to date as best as I can and periodically improve upon it. But first of all, here's what it does. And there's a video out on that website. I normally, if this was the full-length course at SIGGRAPH, I would show it at this point. I would show it running on my laptop. It's not meant to be overly tricky and complicated. There are two modes. It's a cube no matter what, but there's two modes. And in one mode, ka-ching, it's doing blended colors, and in another, it's doing ka-ching, textures. By the way, that is Zelda, the Vulcan dog, who was a puppy when I first started to make up these notes, and she's a whole lot bigger and a whole lot faster now. And when I said you may hear dog barking in the middle, well, that's Zelda the Vulcan dog. And this is what the program does. If you hit the L key, you toggle the lighting on and off. If you hit the M key, you're toggling the mode, which is textures versus colors. P to pause the animation, Q to quit, yeah, R, and so on. It's all there. All right, some things about the notes. I've written everything out in appalling longhand. And again, me personally, I hate it when I go look at sample code and I can't figure out where things came from. Oh, there's this secret helper function we didn't put in here. Oh, there's this secret library we're using, and it sets some things that you now can't find out how they're set, or you have a hard time finding them. I've written out everything in appalling longhand, and largely this is a measure of the fact that I teach this at Oregon State University, and college students really need to see things in appalling longhand before they try and simplify it on their own. Everything is in one CPP file. Again, a very bad programming practice, but I wanted you to be able to find everything. The geometry data actually is a separate file, just so it doesn't clutter, but it's just the geometry data. We could have hidden complexity, but we didn't. We're showing you everything. Set up, as I said a moment ago, I've set up most of the structs every time they're being used, even though they could have been set up once and never reinitialized again. Okay, it's just crazy to do it the way I've done it, except for if you're presenting this to people who are seeing it for the first time. And at times, I've actually set elements of the structs that didn't need to be set, that given the mode the function is being called with, those elements aren't being looked at, but I set them up anyway, just so that you could see what goes there. There are great uses for C++ classes and methods to hide some of the complexity. I know a bunch of people who are working on their own versions. Probably one of them will eventually emerge, will bubble up to the top, and we'll all use that to simplify this. But as far as I know, there's not one standard. And if I did use those here, you wouldn't be able to see really how things happened. I put persistent information in global variables. Again, I know you're not supposed to do that, but I'm just trying to make the whole thing as transparent as possible. At times, I copied lines from Vulcan.h into the code as comments just to show you what certain options are. Like, oh, I set it that this struct element to this, but here are the 10 things you could have used. Okay. Again, I've divided this up into pieces that make sense to me. That's that list with all the numbers. But of course, you should adapt it to the way you like to think. This is what the main program looks like, which is deceptively small. However, when you call the initialize graphics function, a whole bunch of other initialization things get called. So yeah, that's how this starts out with a small number of lines of code and then branches out, sort of like throwing a sponge into the water. It just goes and expands out. Here's the middle loop, and I'm using Glfw as the interface to the window system. That seems to work really well. It's got the functions you need, and so we're doing that. And so we're just running through a while loop in the Glfw world. Here is what you can discern by looking at the names of variables, okay? Anything that begins with capital V lowercase k is part of Vulcan, and it's a type def, probably a struct. It's probably a struct that's been type def to a name. You can kind of tell by how it's used, but look for capital V lowercase k. Function calls in the Vulcan library are lowercase v, lowercase k. Capital V, capital K, underbar is a constant. Okay, it's not a pound define, it's a const variable, which is good. Okay, so yes, pay attention to this convention because that will help you. My conventions in this code are any function that begins with a init means that something's being set up and it only needs to be set up once. Okay, there is a reset function that sets things up multiple times or whenever you want it, but init functions are set it up once. Okay, the number after init gives you the ordering from that list of numbers. And so for instance, there's an init01 function. And again, that's there to help people looking at the code for the first time. Oh, I can relate it back to the list. Okay, in the source code, after main comes init graphics, and then after that come the init functions, the other init functions in numerical order. Again, easy to find them, I hope. Find in a function name means that something is being looked for, something is being determined. Fill in a function name means that some data is being supplied to Vulcan as you're asking it to fill some Vulcan information into a data structure. And again, those are my conventions, not Vulcan. Throughout the code, you'll see capital in and capital out. They are actually pound defined to nothing. But there are a lot of places in Vulcan where a pointer to a struct is given to a function. And sometimes the pointer to the struct is given to the function because it contains information that you needed to supply into that struct. And sometimes the pointer to the struct is given to the function so the function can fill that struct with other information. These are there to tell you that, which is which. And so there are sometimes a pointer to a struct is passed in and it says in front of it. And that's your clue that it's information you've provided and you're giving it to the function. And sometimes out is there and that's the clue that the function is filling something. There's no significance to this. This is my convention, not Vulcan's. It's just there as being helpful to looking at the function and in one glance kind of figure out what the function's up to. These are the files that are in that sample 2019. By the way, sample 2019, the 2019 doesn't mean it was written then, it means it's done against Visual Studio 2019. These are the compilers for the shader. We'll come back to that. If you're in Visual Studio, double click here. That will bring it up. Yeah, there's a bunch of stuff in here. We'll also talk about what this GLM thing is. I've tried to just throw everything in here you could possibly need. The picture of the puppy, the .h files. Again, trying to make this as easy to get into. This is something I wrote. It's just if you print, many of the Vulcan functions return a status. And if you see what the status is, well, if you go back to vulcan.h, you'll see that these are the statuses that are defined. However, those little teeny phrases don't really help you much, or maybe don't. And so I've created other phrases. So if you call this function with the status that you get out of the Vulcan function you just called, this should print out a more meaningful string. And certainly feel free to change the strings if you have ways of making them more meaningful. And if you do, actually, let me know. I'll go change mine. Yeah, so here's the function. Just pass in your VK result. The status has come back as type VK result. Yeah, these are some other things I threw in there, largely for me, but I didn't take them out. All right. We could start at the beginning like, oh, here's how you set up a Vulcan program. But I know what we all care about. We care about drawing. And especially if you're learning Vulcan and you're thinking, oh boy, I'm going to need to convert from OpenGL to Vulcan, you're probably thinking, oh, I sure hope the drawing doesn't look all that different. And the good news is it really doesn't. If you've been using Vertex buffers in OpenGL, then the drawing will seem pretty familiar. So let's go look at that. First of all, there's topologies. Oh yeah, great. You already know this from OpenGL. GL begin. And there's a lot of them that are familiar, like points, lines, the pairs, line strip. There is no line loop. We really didn't need that much anyway. You just replicate points. There's individual triangles, there's triangle strips, there's triangle fans, okay? Here's the list. Now, there are some you don't see. You don't see GL underbar polygon. Well, that should never be used even in OpenGL. That's tremendously inefficient. Quads are gone. If you've got quads, break it up into 2 triangles. Quads were messy anyway because there was no guarantee they were planar or convex, whereas triangles, you're guaranteed they're planar and convex. So these are your topologies. If you're using other topologies out of OpenGL, just write a little converter that converts them into these. And here is the list. There's a type def called VK primitive topology, and you can see some of these in there. Notice the with adjacency is in there as well. You know, this topology was really created for geometry shaders. I'm leaving that out right now because we're not going to talk about geometry shaders and tessellation shaders here, but if you're familiar with them in the OpenGL sense, they work exactly the same in Vulkan. So let's draw our friend the cube. Now the cube has 8 vertices, and I can list them here, and each vertex has its own color, and I can list it there. And if I'm doing an index drawing, I can put the indices here. Notice there's 2 ways of drawing. Is I could list all the vertices. Now here I've listed just 8 vertices, but if I'm drawing each triangle separately, well, each vertex is really shared by what, 1, 2, 3, 4, 5, 6 triangles. And so I could list all the vertices I need, but I'm going to list each vertex 6 times. However, it's probably fastest to draw that way, although it takes up a lot more space in the buffers you're going to create. Or you could do it with the indices and list the vertices once. I'll show you both ways of doing it in Vulkan. Here's what you find in the vertex data file. You'll see that there's a struct. Oops. Yeah, every so often the pen triggers a page change, sorry. And this is doing that direct drawing. It's listing all the vertices. So for triangle 0, 2, 3, here is vertex 0's coordinates, vertex 2's coordinates, vertex 3's coordinates. The other things in here are the normal vector, the perpendicular, the color, RGB, and the texture coordinates. And so that's what we've got here. And so we've listed everything for vertex 0, and then 2, and then 3. And the next time vertex 0 is used, well, it's going to get listed a second time. Those 4 lines for vertex 0 are going to get listed again. And again, you can see that if you go look at that sample vertex data file. And so really, this is the drawing process that Vulkan follows, and it's like vertex buffers in OpenGL, is we're going to have the vertices all lined up in GPU memory, and we're just going to pump them on out. And we're going to use the triangles topology so that every 3, 0, 2, 3, here, 0, 3, 1, there. So every 3 of them form a triangle. And by doing this full struct, we know also what the normal vector is, what the color is, what the texture coordinates are. So yeah, great. This is everything we will need to do the drawing. So if you use vertex buffers in OpenGL, this should look very familiar to you. And that's the good news, is a lot of the Vulkan setup is different. But the drawing, the stuff in the middle that you really care about, is largely what you'd expect. And of course, there are probably tons of ways of writing your own little helper functions that help set this up. In that sample vertex data file, oh my gosh, it is set up so verbosely. How do you get this in? Well, in Vulkan, the word buffer means a chunk of graphics card, GPU memory that you're going to put your own stuff in. And so in step number 5, and the function init05, initialize the vertex data buffer, okay? And it is going to use the fact that in that vertex data file, it knows how big that buffer is, and it's going to go and create that. Vertex buffers are actually just a special case of data buffers. And data buffers were meant in Vulcan to hold anything. The use of whatever's in there, the use of the bytes that are in there depend on, well, how you're using it, what functions you point at that buffer. So there is a init vertex data buffer, vertex buffer function in the code, but then there's also an initialize data buffer, and Vertex just turns right around and calls it. Why not use the init data buffer? Because the data buffer wants to know how these bytes are being used, and so the init vertex data buffer function tells it that. And so here's one of the Vulcan consts. Yes, the buffer is going to be used as a vertex buffer. But other than that, a vertex buffer and a data buffer are no different. Here's how you set up the data buffer. This again is the Vulcan style. This is a type def of a struct. Here's what you put in the struct. We're now calling create buffer and using that struct as an input. There's that in I was telling you about. Here's the out, and it's returning to you some information about the buffer. And it's really this information that you need to keep around, because every time you use the buffer, it's that information that you're going to need. A couple of things to notice here. Notice that all these structs have a .s type element, and in there you put the kind of struct it is. This is a nice error checking thing. It keeps you from passing the wrong type struct into a function it was not designed for. There's a p next, which most of the time is just null. That's really reserved for future expansion. There's a .flags. Most of the time that's 0. That's largely reserved for future expansion. There are a couple that use the flags, but most of them don't. But you will see that in every single struct. And again, if you were writing your own C++ class to create a buffer, you could do things like have this automatically filled in within the class, and you would never have to see it again. So again, feel free to come up with your own efficiencies in the programming. Here are other things that are going on. You need to do some things with memory. And so it's going to take the pointer to the buffer you've got, and it's going to tell you something about the memory requirements. And then when you go to allocate the memory, it needs that information, which then goes to here, which then goes to here. And so creating a buffer is actually a two-step process. You create the buffer. This is step 1 up here. And eventually you get down here and you allocate the memory for it. So that's sort of the malloc in the GPU memory. Okay. And then you bind the buffer, bind in the same sense that Opengl uses, and now you're ready to go. Okay, we will come to the pipeline a little later, but for now, know that a Vulcan program, a Vulcan pipeline, they call it the pipeline. It probably should have been called the state or the context. But it's called the pipeline in Vulcan. It's essentially a large data structure. And it's that big, ugly block diagram you saw at the beginning. And so in C, C++, if this is what we have, and we do, here's how you tell the pipeline data structure about it. Okay. Again, we will come back to this in a little bit. Well, okay, here's a little more information. I did want to point out that because we've got 4 pieces of information right here, we have to create 4 sub data structures. There really are, there's an array of structs here, and each 4 things we've got 4 structs in that array of structs. And here's where we're telling it what we've got. Oh, that first thing is a vec3, and the next one's a vec3, and this last one's a vec2. And here's how you find where you are in the struct. And I think everybody's familiar with the size of in C. However, there is also an offset of, and that tells you how many bytes you are into this struct. So offset of the position, well, that would come back as 0. And then offset of the normal, offset of the normal would come back as 12, because the position occupies 12 bytes, 3 times 4. And so on. You should always use offset of. Do not hard code these offsets, okay? Because if you change the struct, then offset of will continue to work correctly, okay? And these are other things that we're going to talk about when we get to the pipeline. But again, here's how we tell it about those 4 elements in the array. Here's how we tell it about binding the vertex descriptions. Again, I don't want to discuss this now because we're going to do it in more detail in the pipeline data structure, but I think it's worthwhile a little bit to say, well, if I'm drawing in this way, how is it I'm going to tell Vulcan what it is I'm doing? Well, okay, here's how I'm going to tell it what I'm doing. There is finally a VK create graphics pipeline function. And yeah, you remember that ugly block diagram. Well, here's where all those pieces of the block diagram all finally come into play. So yes, this is going to work, but we're going to come back to it. Yeah, okay, I'm tired of saying that. All right, what if we want to do indexed? Okay, and there is an array in that that vertex data file that has this information. So vertex 0 goes to 2, goes to 3, and so on. In that case, you would just need the individual vertices. You would not need to send each vertex in separately, send it in 6 times. You would just need to send it in once, and then these are indexes into it. And so here's my stream of indexes, and it would look them up, and then the vertices would still flow into the graphics, just like before. So again, if you're using index drawing in OpenGL, this should look very familiar. How do you do this? Well, easy. You say to Vulcan, bind, that is connect up the vertex buffer that I need, and I say bind, connect up the index buffer that I need, and then I say draw indexed. And so just like OpenGL, there is this concept of what's the current buffer? What's the current buffer that I'm using? And that's here. So when I say draw indexed, I don't have to say which vertex buffer, which index buffer am I using. It already knows. It's the ones that are currently bound. So throughout your drawing function, you're going to bind and rebind vertex and index buffers, and then just keep saying command draw or command draw indexed. The index type is how many bits there are in the index. The index could be a 16-bit unsigned integer or a 32-bit unsigned integer. You tell it here, and then you make sure your indices are created that way. This way you save half the memory if you have no more than 65,000 numbers from 0 to 65,000. Notice there are things called offsets in here. Okay, there's an offset there, there's an offset there. What are those about? Vulcan gives you the ability, if you want to put more than one set of things in a certain buffer. So for instance, if I have two objects, I could create two separate vertex buffers, or I could create one big vertex buffer that contains the vertices of both. And if you want to do that, well, basically that saves you a bind. It saves you having to bind the second buffer. You bind one buffer and then you use it twice. And the offset is what lets you use it twice. The offsets are how many bytes deep into this buffer am I going to start? Okay, so it's be like in C saying ampersand array, square bracket, index, square bracket. Okay, so that's what and you'll see the offsets all through the Vulcan functions, and that's what they're there for, is you can double duty certain buffers to avoid the overhead of binding. And of course, it doesn't have to be 2, it could be 10, could be 100, but it's up to you to manage that. It's up to you to provide the correct offset. And so in the code, here's how you set up the index buffer, and it looks just like the other one, except here we're declaring our usage for it is going to be as an index buffer, and then you go set up the vertex buffer like this, and you set up the index buffer like this, and it really looks just the same as the direct, where you're not setting up the index buffer, only you're doing it twice. So when we get to commands, what you'll see is there are a whole bunch of functions that begin with vkcmd. Those are commands to the graphics. So most everything else is set up, but those are actual do it in the graphics. And so that's why we've got the vk command bind, because you're going to do this on the fly into the graphics. And that's why we've got vk command draw indexed here. And again, these are examples of using the index count and the index offset. I ought to point out that sometimes a point that is common to multiple faces has the same attribute. So for instance, this vertex right here, regardless of which face it's on, is always yellow. That's just how the code was set up. However, this face, same vertex, this vertex in the texture mode has different S's and T's. You've got to be careful of this, and this is no different than OpenGL drawing. You've got to be careful of this, because if you want to do index drawing, well, then certain things don't work or don't work very well. If I'm doing index drawing, then I'm assuming that this vertex has one struct, but I need a different S and T texture coordinate for this face, then for this face, then for this face. Okay, just be real careful as you're setting up your data structure. Sometimes this controls whether you're going to do that direct drawing or the indirect indexed drawing. Yeah, and if you don't get it right, here's what you get. You get something that looks like this, because for at least some face, it's now pointing into the wrong place in the texture. All right, let's talk about shaders. And by the way, if we were doing this at SIGGRAPH, there would be places where I would say, oh, let's take a break. Let's go to the bathroom. Let's just take a breather for a minute. Of course, feel free to take a break anywhere you want, because you can just stop this. So, you know, this would be a good place to take a break, really, is, okay, we've discussed drawing, but I'm not going to take a break. Anyway, let's talk about shaders. when Vulcan was being developed, one of my huge fears was, oh my gosh, they're going to invent a totally different shader language, and now the hundreds of GLSL shaders I've already written are all going to be obsolete for Vulcan. Well, mercifully, they didn't do that. And so we are using GLSL in Vulcan with some changes. Just a second, I'm going to take my break and take a sip of coffee. So far, so good on the barking dog. This is a shader view of the graphics process, the graphics pipeline, the hardware pipeline. Vertex shaders, tessellation shaders, geometry shaders, and fragment shaders. And that is still in use for Vulcan. And you can see that actually if you go to the type def of this enum, you can see these things listed. And there are places in the Vulcan code where you need to specify, and here's something I'm setting up, and here's the shader type I'm setting it up for. And here's how you get that. It's things like pipeline stage vertex shader. By the way, in Vulcan type defs, anytime you see a bit, underbar bit at the end, that means that these things are allowed to be ORed together. If you don't see that, that means it's a value, and you pick which one you want and you use it. But anytime you see underbar bit, and you notice this is 1, 2, 4, 8, and so on, they can be ORed together. And so if you're setting up some property that both vertex and fragment shaders can use, you can just OR those together. So notice the pattern. All right, here are the differences between GLSL that you know for OpenGL and GLSL for Vulcan. One, there is an in the compiler for the shader, the Vulcan compiler, there is automatically a #define injected into the code for you. And that's great, because if you've got some differences in your OpenGL version of that shader and your Vulcan version of that shader, then all you have to do is do if defs. If def Vulcan, then do it this way, else, else, do it this way, end if. And so it's great. And besides the fact that it's a Vulcan, there's also this version number. This would be 1.0. So you can have 110 for version 1.1 and 120 for version 1.2. Yeah, that works great. So I'm really glad they did that. So I've done this a few times now, and it works wonderfully. They changed the name of the vertex and instance indices. And we're going to talk about instancing in a little bit. And so if you don't know what that is, this will make sense after that. But OpenGL uses those built-in variables to look like this. Vulcan uses the same concept to say that. They really were never IDs, they were always index, and they were indexes into something. So it's a correct use of the terminology to call them index. Frag color. When you learn GLSL for the first time, you're very reliant on frag color. Frag color eventually in OpenGL GLSL meant that it broadcasts that value to all color attachments. If you wanted it to go, vec4 to go to just one color attachments, you would set up a separate variable for that. Okay, frag color in Vulcan actually behaves even different from that. And so I recommend you don't use frag color at all, is just explicitly declare what output vec4s you want coming out of the fragment shader. There's some other interesting differences. You can actually separate the sampler, the parameters of a texture from the texture data. Okay, and you do it like this, and then you combine them both right here, and you still pass in, say, a vec2 to index into the texture. This is if you want to specify separately a set of parameters to use and have that apply to, say, all textures. Well, okay, you don't have to change all textures, you just have to change those sampler parameters and include it in all your shaders. The sample code doesn't do this. The other way of doing it, the way that's more common, the way you've seen, where you combine this into one uniform variable, that still works fine. Descriptor sets, this is how you pass in information about your uniform variables. We're going to come back to this because this is super, super important. Push constants, this is a way of just injecting bits into your shader. And I like this. We'll talk about push constants before we're done today. I like this. You basically can set up a push variable in your shader. That's what this is doing. And from your C Vulcan code, you can just inject bits into it. As you can just say, here, take this group of bits, put it in that variable. It better be right. You know, you better have gotten it right in terms of what it's there for, and is it an int or is it a float? But it just injects bits. You know, what could be more fun? What could be more dangerous? Specialization constants, we're not going to talk about those today, but you will see them if you go to the compute shader notes in the full note set. They are a way of injecting things you used to have to make as constants in your compute shader. Now you can set from the outside. So I like that a lot, but we won't be covering that today. Okay, all non-sampler uniform variables must be done in blocks. And so here is a way that, well, you would probably do it too, but the sample code does it, is it's putting all the matrices together, and it's done it as a block. If you wanted to send each one through separately, well, you couldn't unless you put each one in its own separate block, which would be tremendously wasteful. Okay, all non-sampler uniform variables must be in block buffers. And so here in the sample code, there's more lighting information that gets set. But if you were just setting the light position here, you would still have to put it into a block buffer. Samplers are the exception to that, and you'll see this in the sample code. It's allowed to keep those out of block buffers. In fact, I think it has to keep them out of block buffers. So that's a difference. Okay, here is the part about the shader compilation that I alluded to a little earlier. You half compile your shader, and by Opengl requiring that GLSL shaders be created from source at runtime, which is the original paradigm, they created problems for software vendors. You know, one, you had to ship your source code with your application, which sort of exposed all your secrets to the world. And also that full compilation at runtime was a way of slowing down your program. That is, your program couldn't really get up and running until all those things were compiled. Well, okay, so here comes Vulcan, and Vulcan is going to do this a little bit different. And here's what Vulcan does. As you're doing your development, before you run your program, you take your GLSL source and you run it through an external compiler. And that produces an intermediate format called SPIR-V. Okay, and SPIR stands for Standard Portable Intermediate Representation, which you don't really need to know. And so it produces, in a different era, we might have called this P code, but it produces this intermediate format that is ugly to look at and hard to reverse engineer and so on. And this is what you ship with your code. And then at runtime, there's a second part of the compiler that's in the driver, and it takes the rest, it takes that intermediate code and compiles it into the vendor specific code. So for NVIDIA, it now knows how to make it run in NVIDIA hardware, AMD, Intel, and so on. Okay, and so this solves those two problems. That is, you don't have to ship source code, you can ship this intermediate format, and it's faster at runtime to get everything up and running. So yeah, this is pretty interesting. And the SpearV spec has been around. It was made public even before the Vulcan spec. And so presumably new shader languages are going to be developed, because all you have to do is produce this. You have to produce the SpearV legal format, and it does, you don't care how it got produced. So surely there's other languages being developed. Here's how you do it. And this is I found this to be a hard thing to get used to, because I'm used to just running the OpenGL application and whoa, look at this, everything seems to work. Everything seems to just happen. It compiles everything. But now if you've made some changes to your GLSL and you just run your application, and then you go, what the hell, my changes didn't seem to work the way I thought they did. That's because you didn't recompile. So somehow build this into your workflow. Now, if you're on something with a make file, you can do this in a make file. Anyway, it is, and there's a copy of this executable in that zip file that you can get from the website. But the name of the compiler is GLS Slang Validator. You know, gosh, type that without making any spelling mistakes. And you give it the shader file, and you can tell it where to find include files. You can tell it which stage this is. Is it a vertex shader or a fragment shader, and so on. And then this is the output. And the file name extension is .spv. These are the shader file extensions that the compiler knows about. So if you're using one of these extensions on your shader file, then you don't need to set what stage this is for. But if for some reason I want to say .v for my vertex shader, the compiler won't know about that, and so you'd better set the stage value. Okay, V is for Vulcan, G is for OpenGL, whatever you put there. And yeah, this has become so useful that they've now backed this into OpenGL. So OpenGL you can pre-compile with SpearV as well. And here's off my machine. This is what it looks like. How do you know if it worked? Well, just like C, C++ compilers, like G++, the compiler gives you no nasty messages. That's how you know it worked. If you want to be absolutely certain, it turns out that SpearV files have a magic number of this in hexadecimal, and so you can test that. You can either put that in your code to test it, or if you're on Linux and you do an octal dump, this is what you'll get. Yeah, however you want to do it. In the code that you've got for this class, here's what's going on. There is no built-in Vulcan function for reading in and compiling a shader. Like in OpenGL, you've got to do it all yourself. And so here's what's going on. You give it a file name, and it reads, well, first thing it does is, this code does, is it reads in the first 4 bytes and checks it against that magic number. And if the magic number is not there, then that means the compilation didn't work. And so there's no point loading it into your Vulcan code, because, well, nothing's going to happen with the shader that didn't compile. So the first thing it does is check against the magic number and get out if nothing worked. This is right out of OpenGL. Is it now looks for the length of the file, it sucks everything into an array, and then it's going to hand that file to the second half of the Vulcan compiler. Well, what really happens with that is there's a type def called shader module, and it's going to just simply fill that with information. And so here is the information on the shader that we just slurped in. So here's the array that we read the shader bytes into. We call vk create shader module, and then it returns back to us a filled structure, which we're going to use later. And to use it later, we're going to provide that to the pipeline data structure. And the moment you finalize the pipeline data structure, that's when it does the second half of the compile. Notice that the first half of the compile is where syntax errors get handled. And so the second half doesn't have to do any syntax errors. If you make it to the second half, then you're guaranteed that the syntax was correct. And so all the second half has to do really is produce the code. Yeah, so here it is in the whole big ugly pipeline block diagram. We're creating that, we're passing in that module. I suppose we could have put another arrow out here saying the file bytes go in there. But anyway, it fits into that overall state pipeline data structure. If you want to see what the SPIR-V looks like, you can have it write it out. Now, SPIR-V itself is a binary format. So if you just try and read the .spv file into a text editor, it'll just look ugly. But if you say -h, it will write it out into a file that you can text edit. And so, yeah. However, other than just nerd interest, I can't think of any good reason to do it. But, you know, nerd interest, that's justification just on its own. So have at it. It is kind of interesting. You know, if I had something that looked like this, here's what the SPIR-V looks like. Well, here's what the text version of the SPIR-V looks like. The binary version is just gibberish. Yeah, more, and so on. Google has something called the Shader C project, and they've written another compiler, and it works the same way, and it produces a SPIR-V file. It's got some really nice features in it. So start with GLS Lang Validator, but once you get going, you might switch over to Shader C or GLSLC and experiment with that. Okay, we use it that way all the time now. All right, so that's it about shaders. You now know how to write shaders, and you have some examples in the sample code. Let's talk about data buffers. Okay, because we really gave that kind of a short treatment when we were talking about the vertex buffers. And so I want to come back to that because there are a lot of uses for data buffers. It's not just for drawing information, vertices and indices. It really can be anything. It really is just a group of bytes in GPU memory. You know, in the database world, people like to call this a binary large object or a blob, meaning it's a bunch of bytes. Yeah, use it the correct way and everybody will be happy. So this is the workflow for creating and using a data buffer. Okay, and we saw this before when we were making the vertex buffer. There's a create buffer, but to call that, you need to know how the buffer is going to be used, and you need to know the size in bytes. And creating the buffer doesn't allocate the memory. And so if you, if you leave off this step, bad things are going to happen, okay? Understand that create buffer does not allocate the memory, it just creates the buffer data structure. Okay, now we ask it, if we have a buffer that is going to look like this, what are its memory requirements going to be? This then gives us back what kind of memory it should go in and the size that it should be in that memory. That then flows into a struct called memory allocation information, which then flows into the allocate memory function. Okay, and so that returns back a handle which we can combine with the buffer data structure when we go bind that buffer memory in order to use it. Now, how do we use it? In OpenGL programming, depending on how you've gone and filled your vertex buffers, you may have done memory mapping. Memory mapping seems to be the Vulcan way of filling a data buffer. So let's look at this whole process in a little more detail. So here's creating the buffer. When we call create buffer, this is the struct we want to send in, and this is the buffer information we want to send out. And so here is the buffer information that's going to get filled. This is the usage. Okay, what are we going to use this for? Notice these define, and these are the possible defines, but they end in bit, which means they can be ORed together. And so if I wanted to use this set of bytes for two different things, I could do it, just OR those together and let Vulcan know. So now we have the buffer. We take that buffer and we ask, well, given that buffer information, what memory requirements are there? That fills this structure, which gets used here. And there's a special little teeny function that's in the sample code. Yeah, okay, I violated my own rule on helper functions, but it's so tiny and it's right there. There are two types of memory in Vulcan. Memory that's host visible, meaning the host can fill it, and memory that is really reserved for the device. And when we get to textures, we'll use that device memory for textures. That is the super fast stuff. Memory that's host visible presumably is slower, but the host can see it, your CPU can see it. So here we want to find memory that's host visible because, well, we want to fill this from the CPU. Okay, so now we have all that information here. That goes into allocate memory. When we've done that, here's how we make that the current buffer. And then if we want to fill it, we call VK map memory. And what that does is it creates a pointer and fills the pointer with bits that make it look like that's local to the host. It's not. It's over on the GPU. It's in GPU memory, but this makes it look to you and your program like it's local in the CPU. Well, that's cool, because all you've got to do is pretend you're copying from one set of CPU data to another set of CPU data. You're not, but it looks that way to you. So the code is really easy. You can do a mem copy if you want. You can set individual structure elements if you want. Yeah, do that. And when you're done, you unmap the memory here, and you're done. So this is the process for creating a buffer and then filling it from your C program. Here's the little function find memory that's host visible. Basically, it's looking through the different banks of memory you've got, which you can sample and ask about, looking for one that has the property of its host visible bit is set. and that's all that's doing. So it's going through the banks of memory looking for that. So this could have been put into the code. I just pulled it out as a separate function. There is the second kind of memory that's device local. We'll need that when we do textures. And here's how you do that. And again, all it is a different bit pattern to AND with. I did this on my on an NVIDIA 1080 Ti, and here's what I got. And what I found was 2 memory banks that are device local, 2 memory banks that are host visible. This will be different. By the way, the sample code prints this out. So whatever you run the sample code on, it will ask the question, what memory types do I have? And it will print this out into a separate text file. But this is what I got for a 1080 Ti. There is actually another set of functions that I haven't played with enough, but I wanted to put them in here because I've heard such good things about it. It's called the Vulcan Memory Allocator, or VMA, keeping consistent with 3-letter acronyms. And it apparently does all this stuff for you, and apparently makes very intelligent decisions. Not just what type of memory it is, but how much you're asking for and so on. Again, I haven't had time to play much with this, but I'm putting it in here because I've heard such good things about it. And here's how you use it. And here things begin with VMA, but it's a very short path from here's what I want to give it to me. And then when you go to use it, you're going to do the memory mapping again, except you're going to rely on VMA to do it for you. So again, I've just heard really good things about it. So I'm throwing it in here because I recommend everybody go take a look at it. Another thing you'll see in the sample code is I find it handy to encapsulate buffer information together. The problem I was running into is I had a buffer running around and I had the memory pointer running around in the code, and I had the size in bytes running around. And unless I was very, very careful, I would find myself using the wrong size with the wrong buffer. And then I realized, yeah, I really need to set up something where I can guarantee that these things never get separated. Okay, that was this. That is, if they're in there, it's the correct buffer, the correct memory, the correct size in bytes. Yeah. Okay, so yeah, it's like objects. It'd be kind of an object-oriented programming thing. You can pass around just one data item, and whatever you need is encapsulated in there. All right, so this shows you passing in uniform variables. In the sample code, it keeps all of these matrices. Well, every time you move something around, it updates these, but it is keeping them in the same block buffer in the shader, which means if I want to send over the matrices, I just do it all at once. That is, I can't really send over just the model matrix and stick it here. I would have to send them all over and put them there, which implies really that what I'm going to do is create a data buffer. That's how uniform variables are stored, is you create a data buffer and in GPU memory, and you fill it from the CPU. And so here's what's in the sample code. And here is filling the model matrix, the view matrix, the projection matrix, the normal matrix. We'll come back to this, okay, because it's using this package called GLM, and we've got a separate chapter here on GLM. Opengl, when it treats angles, uses degrees. That's always driven me crazy because everything else in the galaxy uses radians. If you put this in the top of your program, it will force GLM to use radians. And say, okay, let's just do the conversion now. But anyway, here's how it is filling the matrices in that matrices structure. And then here's how it's going to write it. And so there's a data buffer. And so here we are setting up, we're passing the matrix structure and creating a data buffer for the matrix structure. And then we are doing a memory mapped copy into that data buffer. That's how we update uniform variables, is we copy them out of the CPU into a place in GPU memory. So what we just talked about with the memory mapping, that's exactly what you go through to change your uniform variables. So it should look pretty familiar. Yeah, so here we're filling the buffer with that matrix structure. So anyway, so yeah, we've seen this. And here we're filling it. Okay, and so yeah, remember that Vulcan to Vulcan and GPU memory, these are just bits. And so when we copy that matrix structure over into what we hope are the correct uniform variables, they're just bits. And so you've got to be very sure that what you're copying matches what you're copying to. And you know, you think, well, how can that not be? Well, the way it cannot be is you make a change to the matrix structure in the C program and forget to make that same change to your buffer, your block buffer in the shader. Okay, and this is really common, is you make a change to one but not to the other, and bad things happen. All right, so that's the end of the data buffer chapter. We're going to get in next, we're going to get into Glfw, that is how do you set up the interface to the Windows system. After that, we're going to talk about GLM, and then we're going to get into some more detail on actually manipulating the things that go on inside this graphics pipeline data structure. So if you're looking for a good breakpoint, this is probably one of the best. Hit pause, go out, go to the bathroom, go get a drink. I'm going to show my solidarity with you by taking another sip of coffee. Oop, getting a little cool. All right, so on with the show. Glfw is a library that interfaces to a Windows system. In OpenGL for years, I just really enjoyed Glut. This is probably a little cleaner and better supported than Glut. So in the sample code, there's an init glfw that does all of this. First, it asks, can we even do this? Well, yes, we can, because we know we're running on Vulcan. We want to create the window, and we want to create the surface, which is something Vulcan needs. We're going to set callbacks. So when you hit a key on the keyboard, here's a function to call. When you move the mouse, here's a function to call. When a mouse button goes up and down, there's a function to call. So this is sort of the minimal amount of stuff that needs to be set up for a graphics window and the input devices. There is a place in Glfw for you to ask, do I have the required extensions? Okay, and there's a way you can ask for that. And so here, when you say get required instance extensions, it's going to return back to you how many extensions that Vulcan has, and it's going to put those strings right here. And then what you do is you go through that list. There are 2 Vulcan extensions that Glfw absolutely has to have, and it's these. And so this will tell you what extensions you've got in the Vulcan you're running, and you'd better see those two. Notice the Win32 is only if you're on Windows. Okay, but this is something you need to do just to make sure that you're on a system that it can actually do what you're about to ask it to do. All right, here's what the keyboard function looks like. This looks like the keyboard callback you would have done in Vulcan or in OpenGL if you were using Glut, say. So if a key has gone down, we just do a switch on the key. If it's M, we're going to change what mode we're in, and so on. So yeah, this should look familiar. If a mouse button goes down, well, in this case, it's just recording what the active button is. Or if the mouse button goes up, it's turning that bit off. But it's recording that so that in the mouse motion, it can see which button's down. And if the left button's down, it's going to change your rotation. If the middle button's down, it's going to change a scale factor. Again, do whatever feels good to you. This is the inner loop for GLFW. There's a function that says, should the window close? Yes or no, 0 or 1 or 0. And if, say, you've hit the X in the upper right corner of the window, this would come back and say, yes, you should close. It would come back as a 1. If it comes back as a 0, you should keep going. This polling events does not block. Okay, and so if there's no events, if the keyboard's not been hit, if nothing's happened with the mouse, then all you have to do is do nothing and go on. Now, what this code does is it samples the time, because it's going to need that if it wants to, say, do this auto rotation of your objects. It updates the scene, meaning it really updates the matrices, and then it triggers a rendering. And so this is a very tight loop. When you get out of the loop, that means you should close. And so these are the things you need to do. And basically, you sort of back out of things the inverse order you created them. And so we want to destroy the Vulcan first, and then we want to turn off the window and so on. So this is at the end of the main program. If you do want to block waiting for events, you remember GLFW poll events does not block. It returns immediately if nothing's been hit. But if you are waiting for something before going on, then you can do this, wait on events. If you want to wait on something, but you want to return after a certain number of seconds, there's a timeout version of this same function. Okay, and if you've done multi-threading, you can break through one of these wait events from a different thread. And this is how you do it. So yes, this all works very nicely and interfaces beautifully with Vulcan. I like it a lot. All right, GLM, the GL Math Library. This is great. And I find myself using this for non-graphics applications. Like if I'm generating some shape I want 3D printed and there's some complex rotations in there, I'll just do it in GLM and be done with it. So I like this a lot. Anyway, it's an open source math producing library. Here's where you find it. There's probably a more updated version than when I wrote this one down. But yeah, get in the habit of using this. This really is a nice thing. Remember when we talked about the difference between deprecated and deprecated? I'm not going to repeat the voice thing. In deprecated open, or not and pre-deprecated OpenGL, we had really nice extra help functions like GLU look at and GL rotate F and scale F. If you're using the OpenGL where things really have been deprecated, And by the way, you should get used to that because in Vulkan, they're gone. In OpenGL, yes, they're gone. It's only OpenGL Desktop where you can still get to them. But now you would just set up these matrices yourself. And fortunately, GLM has created functions that look like the things you were doing with the OpenGL calls. And so, great. Here's how you make an identity matrix. You use the constructor. It's a matrix for, use the constructor. And you start multiplying these in, and here's your model view matrix. So it's really not that much different, except it's not built into the graphics language. Yeah. GLM recommends that you use this syntax so that you're always putting this out here. The reason is they made no effort to use the same letter or two letters at the front of all the GLM functions. So it's not like OpenGL where there's a GL or Vulkan where there's a VK. And so it's real easy that to happen that you've got a vec3 somewhere else in your program. So they recommend you just keep putting GLM : in front of it. But they've overloaded the multiply operator, so you can do things like that or do things like this. Yeah, there's rotate, scale, and translate that are made to look very much like the corresponding OpenGL function. So really, replacing what you knew with GLM is not all that hard. You just need to pass the matrix in, okay? And so in OpenGL, you could do that with mult matrix. I'll show you in a bit how to do that in Vulkan. Yeah, here's the projection matrices. There's the look at. It's here in the sample code. Typically, you put GLM in one place on your machine, and then you point to it. I put it in here just to save you the pain of having to go get it. But really, if you use it a lot from different projects, you ought to put it in one place so that when you update it to the most recent version, every project gets the most recent version. But here, it's there. And if you go to the GLM folder, yeah, you'll see a bunch of stuff. One of the interesting things about GLM, actually, is it's not a library of functions. Everything is done through the .h files. And so when you compile your Vulkan code, you actually are recompiling so much stuff out of GLM. And like, oh, okay. But the advantage of that is this is how it gets to be fairly universal, is you don't have to worry about library incompatibilities. Oh, am I running in 64-bit? Oh, but the library I picked up is 32-bit. Like, how often does that happen? A lot. And so since it's recompiling it with your code, yes, it's got all the same flags. But if you go to the GLM folder, you'll see a whole bunch of these .h files, and that's where these individual things are defined. Here's what it looks like in the update scene function. So if we're using the mouse, that means we want to rotate the scene with the mouse. Otherwise, we want to animate it. If we're animating it, let me do that first. If we're animating it, then the model matrix is going to get filled based on the time variable, which was set in that Glfw polling loop. So the Glfw polling loop asks, what's the current time? And it's used right here. And so it's going to sit there and create a model matrix that represents a rotation of the cube. If you're using the mouse, well, then we're going to grab these variables which were set in the mouse motion function and scale, and we're going to set the model matrix that way. All right, cool. The projection matrix, we're doing this in perspective. So we use GLM perspective. Remember at the beginning, I said in Vulkan in screen coordinates, Y points down. Here's the only place we care. yes, go ahead, do all your geometry as if it was right-handed coordinates, just like you're used to. But right here, invert the y value in the projection matrix. That's all you got to do. That now corrects for y pointing down in screen coordinates. Cool, that's it. Normal matrix, most of the time you think, well, the normal matrix should be the same as the model matrix, right? And most of the time it is. However, it really, really is the inverse transpose, not the model matrix. And so we set the normal matrix separately. And that's why in GLSL there's a separate normal matrix. And so now we filled this matrices struct, and we go fill the data buffer that, oops, right here, we go fill the data buffer with those values. So that's how we fill the matrices and get them over to the shader as uniform variables. By the way, that whole thing about the normal matrix being the inverse transpose, that is a perpetual confusion factor. Like, wait, isn't it the model matrix? Like if I rotate the object, doesn't the normal rotate with it? And yes, most of the time. The difference is if you have non-uniform scalings, if you have used the scale function to say stretch the object, then that is not true. And rather than showing you mathematically, I'm just going to draw a picture of it. So here's an object and here's its normal perpendicular. If I stretch the object, that is, if I scale it in the x direction, I'm going to get this ellipse. And if I scale, if I stretch the normal in that x direction, I'm going to get this. And clearly, this is not a right angle. So something's gone wrong. If I do, instead of doing this, which is wrong, instead of that, if I do this, then I am really going to get a right angle. So if you're not doing non-uniform scalings, you don't have to worry about it. If you just say inverse transpose, you'll get it right all the time. All right, instancing. When we were talking about the commands to do drawing, you saw that there were some instance counts going on. What in the world is that? Instancing is the ability to draw the same object multiple times. Oh, and this comes up a lot, is I wanted, instead of drawing one cube, I want to draw a 3x3 grid of cubes. Well, do I really have to say, put in the same code for drawing a cube 9 times? No, I actually don't. And it's an efficiency thing. Besides being a convenience for you, it's an efficiency thing. That is, I can just say, do this multiple times, and that's all I have to do. And the graphics system will take care of looping through it. And so really it creates kind of an implied for loop that you didn't have to create. And again, you see it here in like the instance count. But if I say, take this cube and draw it 9 times, it's going to draw it on top of each other. Like, oh, it's the identical code. Okay. It's going to draw it on top of each other. Well, that's not what we want. So obviously we need some way of differentiating the instances. And the answer to that is the built-in GLSL variable called instance index. And this was called instance ID in Opengl, GLSL. And index is the correct use of the term. But here's how it would work is this tells you 0 to something what index you're on right now. So if I say I want 9 instances of the cube, this will come back, this inside GLSL, this will come back as 0 to 8. and it'll get called 9 times because it's drawing the 9 cubes the same way. And so you do something. Now, in this one, it's trying to create a grid, and so it's doing some modding and some division, and okay, this is a little bit cheesy. And then it's also using the index, the instance index, in determining the color, and I know you can do better, but this was the example. And so now, if I simply turn on instancing and say I want, well, in this case, 16 as my instance count, and I put the correct code into the the GLSL shader, I get this. And so here we're having them positioned in a 4x4 grid. Why a 4x4 grid? Because that's what the modding and the dividing right here were all about. And that's also what the color change was about. That's going on here. Yeah, so it's changing the green component of the color. And so that's why it's doing that. In this case, the way the shader code was written, it had no impact if you're in the texture mode, but it does here. So this is wonderful for certain applications. And it's so convenient because really the graphics system is doing all the work for you. You just have to come up with the logic of how to differentiate each one of the indices or each one of the instances. There is another way to do that differentiating. It still uses GL instance index. However, what you can do is you could set up another uniform buffer that maybe has a list of colors in it. And again, this isn't hard to set up, right? Because over in the CPU side, you're just going to set up a struct with that array of colors, and you're going to allocate, you're going to create a data buffer, you're going to do memory mapping and copy that list of colors over. And it probably never changes. It's probably the same list of colors throughout. And then when you're in the GLSL shader, you do something like this, is you take that instance index and mod it with 1024, just to make sure you don't ask for something bigger than what the array is, and then use that index to look up the color, and then use that as the color of the thing you're about to draw. So yes, you can pass in tables of characteristics and use the instance index to get the right characteristic at the right time. Pipeline data structure. All right, this might be a moment to go take another break. I'll do the same to show my solidarity with you. So pipeline data structure, we've talked about, it is the context, it is the state. It has roughly the same meaning as context and state in OpenGL, meaning it's all the characteristics that get applied to the thing you're about to draw. Okay, yeah, don't worry if this is small, we're about to come back to it. I wish they hadn't called it the pipeline because in computer graphics, the word pipeline has meant this sort of thing for years. Oh, we're going to do the model transform, then we're going to do the view transform, then we're going to do the projection transform. That's what pipeline has meant for years. That's not what is meant here. Graphics pipeline, and I've changed it to graphics pipeline data structure, is the context or the state. That is, it's the whole set of characteristics that are needed to draw the very next thing. Okay. The graphics pipeline data structure is largely immutable. Yeah, there are sneaky ways of getting it and changing some value, but let's not think about that. Let's think about it as for every combination of characteristics, current color, current transforms, the shaders to use, what the viewporting is, what the scissoring is, and so on. For every combination of characteristics, I need to create a unique pipeline data structure. Okay. And I've heard from some people I know in game companies that at the start of the game engine, they often create like 2,000 graphics pipeline data structures because that's how many unique combinations of characteristics they want to have on tap. Okay, yeah, you got to do it. Now, in exchange for that, what you get is a whole set of characteristics that can be changed on the fly, like WAP, and all those characteristics now take effect. One of the things OpenGL discovered is setting the characteristics one at a time. Set the color, set the transform, and so on is really inefficient. So pipeline data structures are there to set all the characteristics in one fell swoop. All right, so here are the different stages. And here is what is going into the graphics pipeline data structure. First of all, you need to declare the pipeline layout. And why is this? Why do you need to declare the pipeline layout? Well, there are elements of the graphics pipeline, pieces in that block diagram, that most of the pieces in that diagram are a fixed size, like the viewport. The viewport is center and X size and Y size. That's not going to change. Okay, so that the size of what you need to store that is static. But these things called descriptor sets and these things called push constants are dynamic. So when you create a pipeline data structure layout, you have to take into account the amount of information here and here. Okay, everything else is a fixed size. Oops, stop it. Okay, and so that's what's going on here. In the pipeline layout, you can see that you are sending in information about the descriptor sets and about the push constants. Here we weren't using them. So that's why you set the layout first. Here's what goes into the pipeline data structure. Okay, and you look through this list and you go, yeah, I've seen this before. Like in OpenGL, like line width, like scissoring information, like viewport information, like the topology, and so on. And so this is what goes into the pipeline data structure. This should seem pretty familiar, but remember, this is now one unique combination that can be set all in one fell swoop. All right, there it is. If you want, pause or go to this page in the notes and look at it. It is kind of interesting to see what's there and then how it's collected. Like viewports and scissoring is all collected into the viewport state. Anyway, yeah, you can look at it. The sample code assumes that that's what this is really for. The sample code makes the rash assumption that for many things you want to do, the only difference in the pipeline data structures is what the vertex shader is, what the fragment shader is, and what your topology is. That may be a horrible assumption, but it worked. It worked for me. So you can ignore this if you want, but that's why it's in there. That is basically, it set all of these things, and the only thing different it did for each time it was called was you got to specify the two shaders and the topology. So yeah, we're all looking for ways of simplifying our Vulcan programs. So here we're creating the shader stages. In our case, we have two, a vertex shader and a fragment shader. And here's what we read in before and created. So here's where we tell the pipeline shader, the pipeline data structure about the shaders we're going to use. Here's where we're binding the vertex buffer. Here's where we're telling it about the 4 things that are defined at each vertex. Here's where we're telling it about how things are put together. And so here's where we're telling it that we're using the triangle topology. And again, this is there just for interest. Here's where we're telling it about tessellation shaders and geometry shaders, which we're not using. Yep, there's the topologies again. Here's where we're telling it about something called restart enable. And you set it as true or false. It's used with the indexed drawing, the indices at the vertices, and it's typically used when you've got triangle strip or triangle fan topologies. And here's what happens. One of the things computer graphics discovered along the way is that starting another set of vertices, starting another set of drawings has some overhead to it. And so wouldn't it be cool if you could draw your entire object with only one call to the drawing? Well, you take something like this. This is a topology visualization of Oregon, actually. And to do that, we're doing a row of triangles here, and then we're doing a row of triangles there. And so to do this, it looks like we really need to create 100 or hundreds of separate triangle strips. Wouldn't it be cool is if we got over to this edge, if we could wrap around and start this row, and then wrap around and start this row, and put it all in one big triangle strip? Well, you can't, but that's what restart enable is for. Is if restart enable is true, then the graphics is looking for a special index. And if you're in the 16-bit indexing mode, well, basically it's looking for all ones, all 1 bits in the index. And in 16-bit indexing mode, that's all ones. In 32-bit indexing mode, this is all ones. If it finds that, it says stop, pretend we're starting over, and then continues on from there. And so it's really a way of doing this wrapping around. Whoops, here. It's really a way of doing this wrapping around. That's what restart enable is, or that's what restarting is. And so now you can take this and put it all in one big triangle strip that is capable of sort of carriage returning to the next line. So that's kind of cool. And that's there. Viewport information. Yeah, this is like GL viewport in OpenGL. That goes here. Oh, and there's scissoring information too. And there's a big confusion usually. What's the difference between viewporting and scissoring? Viewporting operates on vertices. It takes place right before the rasterizer step, and it's a transform. And so if you change the vertical part of the viewport, okay, well, that causes the entire scene to get scaled. So if this is my original object and I change the vertical part of the viewport, basically I am squishing the whole object. Scissoring, on the other hand, operates on the fragments, or the pixels, essentially. And what it does is it causes the entire scene to get clipped. So basically, it doesn't squish the object. It essentially just write protects this part of the screen. This is useful sometimes, like if you want to put a text block there under the object, but you don't want to distort the object, and so you scissor it so that you have an empty chunk of screen to put other stuff. But anyway, so they're both given in this part of the pipeline data structure. Here's information on how the rasterization will take place, like the polygon fill mode. fill the polygons, either fill them, turn them into the edges, or turn them into the vertex points. Here's information on culling front, culling back, and even a definition of what front and back are. There's a depth clamp. Depth clamp is interesting in that fragments that would normally have been discarded because they pass through the near clipping plane, they're too close to the viewer, it will actually instead appear to cap them. Yeah, this is nice. If you normally zoom in too far on something, the graphics will reveal to you that it's really a shell, not a solid object. Polygon capping preserves the illusion it's a solid object. Depth bias, it's a way of preventing Z-fighting. This is Z-fighting where two things are at exactly the same spot, and so it's having a hard time discerning which one is which. This brings objects either a little bit forward or a little bit back, so it prevents the Z-fighting. Multi-sampling, and multi-sampling is one of the things we won't have time to get to, but it is in the big set, the full set of notes on the website. But it's essentially an anti-aliasing technique where you do subpixel rendering. This helps you enable that. Here we've got blending. If we want to do some blending on the way out of the fragment shader into the frame buffer, here's what you do. I said that this pipeline state is immutable, but there actually are secret ways you can go stuff values in. These are the ones you can change on the fly. That is, I could create a pipeline data structure with one unique combination of variables, and then I could say, but change the line width to this, and now use it again. Those are called dynamic state variables, and these are the ones you've got. And then this is the Vulcan code for using them, for setting them. The stencil buffer is another frame buffer. There's a lot of interesting graphics algorithms that use this. You can use it, say, for a magic lens. It's really a way of sort of programmably write protecting or write enabling parts of the screen. So here, when you're rendering the objects as solids, you write protect this window. And then when you go render the wireframe versions of the objects, you write enable that window and write protect everything else. So so the stencil buffer, it is exactly what it sounds like, really. You know, you do some painting, you put down the masking tape, and now you can be very fast about your painting, and certain areas won't get painted on. That's what a stencil buffer is about. Yeah. You also can use it to do much cleaner edges. If you just draw edges on top of polygons, you get this Z-fighting effect right here. You know, it looks like stitching, but it's really Z-fighting. Whereas if you use the stencil buffer to write protect those areas and then draw the edges, you get really clean edges. You know, this versus this. And if you do the same thing and do the background, the interior of the polygons is the same color as the background, you really get a very nice hidden line removal look to it. I really like that. There's a certain crispness about hidden line removal I like. So there are places in the pipeline data structure for you to set up all this stuff with stencil buffer information. And I'm not going to go into that because it's the same as what's in OpenGL, just asked for differently. And here's where it all comes together. This is the final ultimate create the pipeline. Here's where it writes the pipeline into. Presumably you've got a whole bunch of these. Presumably there perhaps an array of those structs so that you can loop through them and load them when you want. But the important part is for the struct that we're creating right now, here is where all of those blocks in the block diagram come together. That's what all these ampersands are, is all these blocks in the block diagram are now coming together to create that one unique combination. And then when you're actually sending commands into the graphics hardware, you bind a particular pipeline like that. And so the mode you're in is you bind a pipeline, do some drawing, bind another pipeline, do some drawing, bind another pipeline, do some drawing, and off you go. And again, why do you need a layout? Well, most of that graphics pipeline data structure are fixed size things. Again, like the viewport, this is all the information you will ever need to specify a viewport. You will never need more or less information than that. And so in the creation of the layout of the pipeline structure that you're doing right now, those things, it already knows how big to make them. However, descriptor sets and push constants are different. They are variable sizes. You know, it's sort of like, here's a variable size pipeline block and I want to plug it into here. Well, okay, once you know the size of this, now it can create the right number of bytes for this particular pipeline data structure. And so that's what this is all about. That's why it does it this way. All right, so we have been talking about this thing called descriptor sets all along. In this next chapter, click, we're going to get into what those descriptor sets actually are. So in Opengl, Opengl puts all its uniform data in the same set. So for instance, you might write a shader that looks like this. And you say, the model matrix, bind that at position 0 in the uniform variable table of variables, okay? And each one of them gets updated one at a time. I could update the model matrix, then I could update the view matrix. What Vulcan has done with this is it has allowed you, or I guess really forced you is a better way to put it, into clumping these things so that they can be changed in groups, not one at a time. And so this is another way of gaining some efficiency where sending over little values, little bits of values one at a time is very inefficient. Sending them over in a bigger group is much more efficient. So that's what we want to do. And what we want to do is we want to cluster these things in a very logical way. And so imagine that this is the kind of a logical diagram of our program. Is we're drawing a scene and we're drawing multiple objects in the scene and we're making multiple draw calls for each object. Okay, well, nested for loops, this for loop is going to get executed a lot. This for loop is going to get executed much less often. And so really, whatever uniform variables we need to set for each draw, let's put those all together so that we can update them without having to update these uniform variables. Okay, and so this is sort of the logic behind descriptor sets. There's really two things. Descriptor sets are a way of bundling your uniform variables in ways that make sense. Things that tend to get changed together, things that tend to get changed in the same parts of the program, or same parts of the rendering. And it's a way of sort of creating that nice mapping between what's on your CPU and what's in the GPU. Okay, so this is sort of the logic we look at when we think about descriptor sets. And so in the shader code, all right, here is set 0. And it's the matrices. And here is set 1. And in the sample code, there's more lighting information. I just did this here in the notes to show that you could put just one piece of information. And here's some of the miscellaneous stuff we need to know about. This set equals, this is something new in Vulkan. The layout, the binding, that was all in OpenGL. And so you should be used to seeing that. But allowing these things to end up in different sets is something new to the Vulkan API. So I mentioned that one purpose of the descriptor sets is to create a very logical, sensible bundling of your uniform variables. The other is to create some sort of translation data structure where you can go from your C program to this cluster of bits that are sitting in GPU memory to the variables in your shader that those bits represent. And so the descriptor sets will not only break things up into sets for you, but will describe what it is you're sending, that is, describe what those bits actually represent. Turns out you don't allocate descriptor sets on the fly. That apparently is slow. So in the process, you create a pool of descriptor sets. This is done at the start of the program. This is done in the sample code in one of the initialization functions. And there are 4 descriptor sets, or there's 4 sets of things. And so we're going to create 4 descriptor sets. And then there's the pool. And you could have a lot of things in the pool. We don't here because we're not doing that much with the descriptor sets, but you could have a lot more in the pool size. All right, I tend to think of the descriptor sets as kind of a Rosetta Stone that helps describe what goes in each of these sets. So let's take a look. So, oh look, init 13, descriptor set layouts. So here is the first descriptor set layout. And you could set these up as arrays. I didn't. So there's just one here in the thing called matrix set. I like naming them for what they really are. This one has to do with matrices. This has to do with lighting. Okay. This one has to do with, well, miscellaneous stuff. And this one has to do with textures. So anyway, we're telling it it's a uniform buffer and it's capable of being accessed by the Vertex shader. Okay, and that makes sense. It's only the Vertex shader that really needs to be able to access the matrices. Is there some efficiency to be gained by not letting the fragment shader see it? I don't know. Presumably there is, or presumably there might be someday. Otherwise, why would they ask you to specify the stage? This one, on the other hand, the lighting, should be capable of being accessed by both, because quite possibly the Vertex shader needs to do something with lighting transforms, but the fragment shader needs to apply it. And so that's why these are being ORed together. There's a underbar bit at the end. Here's the miscellaneous stuff. That's where I was just kind of throwing in anything else that I needed, like the time variable, for instance, which mode I'm in. And so I figure, yeah, we should let all shader stages get access to that. This texture sampler, nah, that's just the fragment shader. And so here we've set up the layouts for the different descriptor sets. Now we're going to create an array of those descriptor set layouts. And that's what's going on here. So we set up a 4-element array of descriptor set layouts, and now we're taking each one of these separate layouts and bringing them in and setting up into that array of descriptor set layout structures. When we were setting up our pipeline layout, because the descriptor sets, the size of the descriptor set data structure depends on how many buffers you've got in your buffer blocks you've got in your shader. This is why when we set up the pipeline layout, we have to tell it about the descriptor set layouts. Okay, so that's why this is done before you're allowed to create the pipeline layout. This, I can tell you, is a dangerous part of your program, because this depends on getting those layouts correct. And if you go change your layout, you want to add one more block buffer into your shader, there's a couple of places in your code you need to reflect that. One is setting up the descriptor sets, and one is right here in the pipeline layout. This is really probably bad practice, is to hard code that number 4. It's much better to put that number 4 in some kind of defined constant, so that when you change it in one place, you change it in lots of places. Again, I can tell you this is a very dangerous moment in your Vulkan programming. All right, oops. All right, so now we want to initialize the descriptor sets. Okay, so we've got those descriptor set, that array of descriptor sets. And here's how we're setting up the descriptor set information about, well, what is in the buffer? So in this descriptor set, here is the name of the buffer we've created for the matrices. You know, and this was way, way back when we were talking about initially creating data buffers. And here's the size of that buffer. And we can put multiple things in the same buffer information. That's why there's an offset. We're not using it. Here is the second one. You know, here is the light, the variable for the lighting. Here's the size. And so we've created these 4 variables that describe the number of bytes that are going into this particular descriptor set. And again, you got to make sure that the definition of these structs in the C program matches this, matches what's in your shader. Okay, this is the rose. These things here are the Rosetta Stone that's going to translate what's in your C to what's in your shader, and the information has got to match. And that's why, of course, you use things like size of, so that if you add things to the struct, then this automatically reflects that. And so now we're going to take each one of those and we're going to create a link to the buffer it's pointing to. And so that's what's going on here. So it's taking the information in descriptor set 0, and it's taking the information in VDB I0, which is right here. And from that, it's producing a structure that describes all of these together. And that's what's going on here. And so what this is about is it's creating a way that you can update those descriptor sets. So each one of these structures has a record of where the graphics memory buffer is and what goes there. And so if I want to update one of these, I call update descriptor sets, and that information, say this information, is all that the update descriptor set function needs to do the write. Okay, take the C buffer and copy it to the right place in my shader code. And you don't have to do all of them. I did it right here and show that all of them can be called. But of course, this is where you optimize and you say, well, at this very moment, I only need to update descriptor set 3. And so you update descriptor set 3, but when you need to update 2, you call this to update 2. So the point is these data structures contain all the information about what's in the C and what's in the shader. And then these update functions can do the correct thing. That's why I sometimes think of this as the Rosetta Stone for what's going into your shader. And when you create the pipeline, all of this information about the layout goes into creating the pipeline. So that now it knows how big to make the pipeline data structure. Okay. When you're executing graphics commands, there's a command for bind descriptor sets. What does this mean? Well, it means that you can actually change the Rosetta Stone. Okay, the pipeline layout contains the structure of the descriptor sets, but the pipeline layout doesn't care what goes in there as long as the structure is the same. And so if you have different values for things, like maybe I'm switching between 2 different sets of matrices. Okay, and what I would do is I would set up both descriptor sets of the matrix, or I would set up both sets of matrices in buffers. I would create 2 different descriptor sets, and then I would swap between them. First, I would bind one, then I would bind the other. Bind one, do some drawing, bind the other, do some drawing. As long as the layout of those descriptor sets is consistent, then it doesn't really matter what is in those bits. And so this is also one of the reasons it's done this way. So here's kind of a summary is, step 1, you've got to create the pool. That's you don't create them on the fly, you pull them out of the pool. Step 2, you figure out the layout of each descriptor set and let the pipeline layout know about that. 3, you allocate memory for the descriptor sets. 4, at runtime or at graphics time, you update the information in the descriptor sets, which updates the information in the shader. And then 5, you can bind and rebind different descriptor sets depending on if you want to change what's in the uniform buffers really quickly. And again, the descriptor sets are variable. They're not fixed, and that's why the pipeline layout wants to know something special about the descriptor sets. And this is how you do different descriptor sets. As long as these structures match, then you can just swap descriptor sets in and out. Okay, so that's how to get information and data across into your uniform variables. And again, make sure what you think you're holding on the CPU matches what you think is in your shader. All right, the next thing up is textures. This is a place I would recommend you take a little break. Now get up, stretch, sip of coffee. Textures are complicated. And I'm going to attempt to decomplicate it by not going through every line of code, but just say, and here's in general what this stuff is doing, and letting it go at that. But send me email if you want, we can talk about it more. Here's where the texture coordinates were before. And this was the structure that was defined for every vertex. So vertex 0 had these coordinates, this normal, this color, and this S and T. And then this went around for every vertex. And this caused the textures to be mapped correctly. That is, somebody painstakingly figured out what S's and T's went to each vertex for each face. And yes, now the textures look correct. Okay, here's how texturing works in Vulkan. And I suspect it works the same way in OpenGL, but so much of this was hidden from us in OpenGL. And now it gets exposed and you go, ah. So again, I'm not going to go through a line of code at a time. I'm going to just say, and this chunk does this, and this chunk does this. Okay, so let's say that we have the texture, the image, over here in CPU memory. We want to get it over here. Remember, there's two types of memory on the GPU, at least as far as Vulkan's concerned. One is device local memory, and that's where it wants to sample the texture from. And presumably that's faster memory, or it's got something special about it so that it can do 4 samples at a time and do bilinear, or 8 samples at a time and do trilinear interpolation, but it's special. And so the texture needs to be in device local memory. In the way is host visible memory. And host visible memory has the property that the host can write to it. The host can see it, the CPU can see it, but it's not where we want the texture to be. And so our process is going to be, we're going to copy the texture, the texels, the colors here, and then we're going to copy them over there. And then everything's good. Remember when we were looking, or I was looking at the types of memory on the system in my office, I found 2 banks with device local, 2 banks with host visible. I also did it on a system that had the Intel integrated chipset. The integrated chipset, every bank of memory was okay to be device local. Only 2 were designated as host visible. What that means, I'm not exactly sure, but when you have something that's meant to run on a lot of different systems like Vulkan is, you've got to do sampling of the system, of the hardware, to see what the characteristics are. And so, yep, here's what it is. In OpenGL, how did we do the setting of texture parameters? Well, we did it like this. How do we do it in Vulkan? We create sampler information. There's a special struct for that. Here's where we do it. Basically, this is the same as that. And from that, we create a sampler. So roughly the same process you're used to, only a little bit more explicit. And clearly, you could create a bunch of these sampler variables that had different combinations of these parameters, and then just bring up the right one at the right time. Okay, there's MIP mapping. MIP mapping works in Vulkan just fine. That has to do with the texels to pixels ratio. So you can set up multi-levels, so you've got a high-res version of your texture, then you average every 4 pixels to, or texels to get a new texture, average down, and so on. And then the trick is figuring out which MIP map to use. So here is the code to set up the sampler. So this process is like we saw a moment ago, except there's really more information to it than just that, just what you provided for OpenGL. Here is the information you need to create what's known as the staging image. And the staging image is putting the image, the texture on the host, or on the host visible part of GPU memory. So here's the information. Yeah, it needs to be a 2D image, needs to be R8, G8, B8, A8. Here's the texture width and the texture height, which presumably you get when you read the texture in. You create an image in the GPU memory. You get its memory requirements, and this is just like creating a buffer. Remember, we created the buffer, but we didn't have memory for it yet. Now we're going to do this, and we're going to allocate memory, and then eventually we are going to bind the image to the memory that got created. And then we're going to do the memory mapping, and we're going to copy the texture colors over into the host memory. And remember, we don't really, or into the host visible memory. And remember, we don't really want that host visible memory except as a path to get to the device local memory. So we've done the necessary but not sufficient part. And you can tell where that is because of this red vertical line. This is meant to identify that part of the process. All right, here we go. This green line is meant to identify the next part of the process, which is to do almost the exact same information or the exact same thing, but in device local memory. So we're going to create an image, we're going to get memory requirements, we're going to allocate memory, and so on. And now we have that device local memory all set up. We now have to do the copy. Well, the copy, I have no explanation why it's done this way, but I'm certain there's really good reasons. The copy is done by issuing a command that does the copy. There is no copy from host visible to device local memory function. It's something that you put into the command, and that's what's going on here. We're changing the structure of the host visible buffer so that it can be copied, and then we're setting up this command to copy it. Okay, we have now done everything we need to do to get the texture to be there. We've created it, we've copied it to host visible memory, we've copied from that over to the device local memory. Okay. And we haven't talked yet about submitting commands to the command queue, but that's what's going on here, is it's taking that copy command and submitting it to the command queue. Okay, so there's one more step. There's a structure called the image view. And think of it this way. The actual image data is here. The image view is a structure that tells, here's how to go get the data. That is, you don't go directly to get the data. You ask this image view to get the data, and then the image view does the right thing. And possibly the image view is going to reinterpret the data. That is, you here in your program, you shouldn't have to care about what this format is. You should just have to say, I want this. And the image view logic goes and gets it and possibly converts it. So here's what's going on. And here's where you tell the image view something about the data that it has access to. And so here we're creating an image view. So once this is done, through here is how you'll get access to that texture. And so really, at this point, you can get rid of the host visible buffer. You can destroy it because it's no longer needed. The texture is where it needs to be in the form it needs to be in. And I found, again, I was having trouble with pieces of information were getting separated. And so I decided I would create a little struct that forces me to keep all that information together. That was really useful. All right, but as long as we're talking about commands, let's go to the command buffers, because that happens here. And so we have seen this just a moment ago. There was something called a command queue, and into that went the command buffer. We don't have time in this class to talk about multi-threading, but this was one of the cool things that was built into Vulcan, is you can have different threads in your CPU program creating parts of your graphics scene at the same time, and the way they do it is they put them in separate command buffers. And then when they're done filling it, they can be flushed to a command queue, and the command queue goes into the graphics. So let's see an idea about how that works. All right, so graphics commands, and these are the VK command. They're stored in the command buffer. So when you say VK command something, it doesn't get executed right then and there. It gets stored in a command buffer. And then at some point you submit the command buffer to a queue, and finally it gets executed. Each command buffer can be filled from a different thread. Again, they record the commands, no work takes place. Yeah, and it works like this. So you can be creating your graphics on multiple CPU threads. There are command queue families, and the different command queues that you have different characteristics. And here in the system in my office, command queue family 0 was able to handle graphics commands and compute commands and transfer commands. And we've already seen a transfer command when we were copying from the host visible memory to the device local memory for textures. Okay, and so and it prints this out in the sample code so you can see what your system does. But the point is, different command queues are set up different ways, and you just have to make sure you're using one of the correct ones. And so just like there's a find host visible memory, there's also this little helper function in the sample code, find the queue family that does graphics. And so it returns to you one that it found. All right, so that's just to make sure you're using the correct queue. You can set up queue characteristics. That's what's going on here. Here's finding a graphics queue. There's a way to set queue priorities. There's a way of looking at the extensions and the device layers. And then there's a way of creating a command pool. The pool is just like the pool in the descriptor set. What they're saying is that command queues are time consuming to create, so don't create them on the fly, just allocate them out of a pool. All right, here's how you set up, you initialize a command buffer. So there's information here. Here we're doing 2 command buffers because we're doing double buffering. We're doing a back buffer and a front buffer. So 2 command buffers will be able to be working together. And here we're going to allocate them and put them in an array. And then here we're allocating another command buffer, and this is the one we used when we wanted to copy the texture. So we're using one command buffer just for that one instance when we needed to copy the texture, and we're using two other command buffers for while we're doing live graphics. That is, we're filling one graphics command buffer and then telling it go ahead and render, and then we're filling the other graphics command buffer while the first one's being rendered. So that's what we're setting up. There are interlocks to be done. That's the semaphores. This is covered in the synchronization notes, which is not part of what we'll do today, but is in the full note set. And as you're doing this double buffering, this fill one while the other's being executed, you need to always be asking it, what's the next one I want? And so that's what the next image is all about. And so we figure out which command buffer we need to fill next, and we call VK begin command buffer. We now do a whole bunch of VK command calls in here, and then we end the command buffer. So we have put those commands in the command buffer ready to be submitted to a queue. And so this is what the process looks like. Here are half of all the VK command calls. And some of these you've seen, like draw indexed. Here's the other half. So there are quite a few of them. But again, these don't execute immediately. They go into the command buffer, ready to be submitted to the command queue. In the process of rendering a whole scene, this is what happens. And what I've done is taken the code from a moment ago and then put some other information around it. Here we're creating a semaphore so that we can get some kind of signal when the next image we want to render into is ready. Here we're going to begin the command buffer. Here we're going to set up information, and we're going to begin something called a render pass, which is where drawing commands go. Here's where we bind the descriptor sets. Okay, so we've already seen that. Here's where we bind the vertex buffer. Here's where we do the drawing. We end the render pass, and then we end the filling of the command buffer. And of course, in a more complicated application, there would be a lot more of these things being done inside this function, a lot more VK commands being called. And then we want to submit that. So we want to take what's in that command buffer and we want to submit it to a command queue. So this is the information about what's going to be submitted to the command queue, and then this is the process. And so ultimately, all of this is coming down to right here, okay? Queue submit. And so the command buffer information is being sent. Here's the command buffer information. It's being sent into the queue submit call. And then it gets submitted to the queue, and then we want to present that to the user. We want the user to be able to see what we've just drawn. So this is the process. This is the rendering process, but it really all has to do with submitting commands into the command queue. Okay, command submissions to a single queue are respectful of submission order. Okay, so the commands that are in the command queue get executed in order, the order in which they've been submitted. And so the driver on your system will execute these commands in a single buffer in the order in which they were put there. However, different command buffers submitted to different queues, the driver is allowed to do some jiggering of the execution order. Yeah, the driver may not, but the driver might. And so it's possible that the driver will go to one queue and pull some things out of there, and then go to the other queue and pull some things out of there. That's not known, and there's no way to ask about it. And so that's why there's a note chapter in the full set of notes on synchronization, because if the contents of one command queue is dependent on the contents of another command queue finishing first, then you've got to maintain that synchronization yourself. All right, so we've talked about the rendering process. You just saw some rendering code, but really to do this properly, we need to talk about the swap chain. And the swap chain is the Vulcan equivalent of OpenGL double buffering. In OpenGL, you have this front buffer and the back buffer. The back buffer is what you're drawing into, and the front buffer is what's being seen by the person sitting in front of the monitor. Okay. In Vulcan, it's a little more flexible. It's something called the swap chain. And you can really think of the swap chain as a ring buffer or a merry-go-round of frame buffers. You can think of it as a ring buffer, and one of these gets rotated into place, one of these back buffers. You update into it. When it's all done, it gets rotated over here and presented to the viewer, and a new back buffer comes into place. A new back buffer comes into place to be updated into. And so they just whirl around in this ring buffer. So if there are only two of them, or I guess only one of them, two of them, then it would look like OpenGL. But this gives you more flexibility because there's much less need to synchronize the front and back buffer. If you're ready to render before, or if the presenter part is done before you're done rendering, you can handle that. There should be at least two in here. I've tried it with 3. I don't see any difference, but I do see people using 3. Anyway, so this is the idea, and this thing is called the swap chain. When you got the surface capabilities from Glfw, there was some information in there that you needed, and you pass that into Vulcan, and it tells you whether Vulcan can support the display hardware you're on. Okay, so this uses the surface information that came out of Glfw, because that was the interface to the Windows system. Okay, so the next thing we need to do is find out about that surface and find out what formats are available. And then from that, you can set what format you want. When I ran that, and again, the sample code will print this out into a file that you can go look at. But here's what I got, and yes, it is supported. Here were the surface capabilities, and what this says is the minimum frame buffers in the swap chain need to be 2 and can go up as high as 8. It found 2 surface formats that are capable of being used, and it found 3 presentation modes that are capable of being used. And so from this, we can make our decision about how we want to set up the displays in the swap chain. So I wanted to, here's the format I decided to use, unnormalized. The colors should be whatever you want them to be. Decided to use this as my color space and decided to use the mailbox format as the present mode. From that, you can create the swap chain. And so that goes in a variable called swap chain. And from that, you can get the images. And remember, we had this front end of the texture that was the image, and that's what you use to really access the image of the texture. Same thing here. We're going to use that to access the image of the frame buffers in the swap chain. And so here we're creating the right number of image views. And so now we've set up the swap chain with the right number of frame buffers and the right number of image views to be able to access those frame buffers. So now, well, this actually is the same code you saw before, but it should make more sense because now we know about the swap chain. So when we're getting ready to render, we acquire the next image. That is, we go ask the swap chain, what's the next empty image I can render into? And it comes back and tells us this is a number between 0 and 1 less than the number of images in the swap chain. So in this case, it's 0 or 1. I begin the command buffer with the correct command buffer, not the one that's being processed right now, but the one that isn't being processed right now. I begin the render pass. I do all the VK commands to do the binding and the drawing. I end the render pass and I end the command buffer, and then I will submit that command buffer to the queue. And then I'll present it to the viewer. And so this is how the swap chain works. And so you can imagine this kind of factory of frame buffers rotating around the ring buffer, being filled, being presented, being filled, being presented. But because you've got this flexibility of the swap chain, things can be done a little more asynchronously if you want them to be. All right, so that is the swap chain. There's 3 things I wanted to talk about before we finish for today. One of them is this magical thing called push constants. And I suspect in the global scheme of things, this is not the end all that I like to think of it as. I just like them. I've just found some just really good uses for push constants. So yeah, push constants are meant to just throw bits into a shader. And you think, well, why do that? Because if you want to update something outside the descriptor set mechanism, it's just a great way to do it. It's got much less overhead than the descriptor set mechanism. The Vulcan spec says that each set of push constants have to be at least 128 bits or bytes in size. I suspect because that's 2 4x4 matrices. Although the vendors are free to ask for more or do more. For instance, the 1080 Ti gives you 256 bytes for a push constant push. I suspect it will end up being more as time goes on because I think people will find interesting uses for this. So where does it show up? Well, it ends up as part of the graphics pipeline, but it ends up here becoming part of the pipeline layout. And like descriptor sets, the push constants can have different sizes. And so you can, the size of the pipeline layout changes depending on your size of the push constants you want to use. All right, how does this show up in a shader? Let's say that we're sending a 4x4 matrix over. We just say layout push constant, and we put the 4x4 matrix here. Now, being a 4x4 matrix, that is 64 bytes. And so what that means is at some point, I'm just going to throw 64 bytes over into this shader. Okay, you have one layout push constant, so there's no question about which push constant in a shader you're throwing to. You do it in a VK command. That is, you do it while you're rendering into the pipeline, and that makes perfect sense. You want to change something like a matrix on the fly. Okay, here are the values, in my case, 64 bytes, that I would want to send over. And I would say 64 right here. The stage flags are which shader gets these. And these can be ORed together. If it's just a matrix, it probably just goes to the Vertex shader. But there's a lot of good uses for that. And here's how you set it up. Okay, there's a push constant range variable, and then that goes into the pipeline create information. So we already saw these, the descriptor sets in the pipeline layout create. Now we have something for the push constants. So when we create the pipeline layout, it's got the fixed size things and the variable size things in it. And here we've told it how big our push constant push is going to be. Here's what I used it for. The first thing is I wanted to animate this robot arm. And so this arm moves. These are pinned together. So the red one moves with respect to the green. These are pinned together, so the blue one moves with respect to the red. And this is standard computer graphics hierarchical transformations. But what I wanted to do was to have one set of code that handled all this over in the graphics as a shader, and then be able to send the information on each arm. And the information on each arm is the transformation and the color and the length. And so here's the transformation, here's the color, length is scale factor. And so that got put into a struct. There were 3 structs. And so the idea was send over as a push constant, set of push constants, the structure for the arm, and then initiate a draw. Then send over the push constants for the red arm, arm 2, initiate a draw, send over the push constants for arm 3, initiate a draw. But the cool thing was, I just drew a cube. As I didn't draw a arm with length, I just was drawing a cube each time and used this scale factor and the rotation matrix to put the cube into a position where it looks like it's supposed to look. Yeah, you've got Tinker Toys, I'm sure. All right, so there's the derivation of the hierarchical transform, which I'm not going to go into. Here is filling those 3 arm structures, and that was done in the update scene function. Here was creating the pipeline layout, and fortunately all 3 of those used the same struct, so I could use the same pipeline layout. And then here it's filling it. So here's where it's doing the transformation for 1 with respect to ground, 2 with respect to 1, 3 with respect to 2, and here it's producing the absolute transforms. So now we've got that. But here's the part I really liked is, all right, let's bind a drawing of a cube. Let's push constant over the parameters for arm 1, and let's draw the cube. parameters for arm 2, draw the cube, parameters for arm 3, draw the cube. I really liked this. I just like the bap, bap, bap of it. And then what happens over on the shader side? Well, we've got a block buffer to match the struct that we're sending over. And here's what it did. And so imagine every time one of those arms went to be drawn, these three values magically got filled. This is our push constant. They magically got filled. And so it used this to scale the cube vertices to the right size. It used this to position the beginning in the right spot. It used this to rotate it. And then it sent the color over to the fragment shader in order to draw it. So yeah, no muss, no fuss. I suspect as time goes on, push constants are going to be deemed more and more essential to doing very efficient Vulkan programming. All right, there's a couple of things before we finish. There's a couple of things I wanted to pick up on. One is the concept of physical devices. Physical devices are the hardware. Okay, they sit right here. A physical device is going to have a logical device interface to it, but the physical device is the actual hardware. And one of the first things you do in your Vulkan program is go ask what physical devices are out there. And it's not uncommon to have, say, both an Intel integrated graphics chip and a discrete graphics card in your system. And so in that case, you would find you had two physical devices. And we looked at this before and we talked about this format of asking for the count, allocating an array of structs, and then filling the array of structs. But this is something you do in your program because when you write a Vulkan program, you never know what it's going to be run on. And so your code has to be ready to adapt what your Vulkan code does around what it finds to do the rendering. And in that case, you probably need to figure out which of the physical devices you're going to render on. Okay, and so in the sample code, it does do this. It prints out the number of physical devices that it found, and it goes and gets physical device properties. And the code doesn't really make any effort to determine which one you want it to use, but it does make an effort to print them out so you can see what you've got. And you can see some of the characteristics. What I've tended to do in other pieces of code is set up kind of a hierarchy. Is if it finds a discrete GPU, it's going to use it. Okay, if it finds an integrated GPU, it's going to use that second if it didn't find discrete. And if it finds this, which it never has so far, they would use that. But again, the logic is up to you, but it's important you figure out how to get your Vulkan code to adapt to what it finds itself running on. And so, yeah, so here's the little logic I had put together to figure that out. And it was printing out information. And on the, well, then I tried it on an RTX 2080. And here's what I got. Yes, it's a discrete GPU, I should hope so. And well, I printed out some of the physical device features, but of course on that card, they're all turned on. But if you do it on other devices, like this was the built-in Intel graphics, I guess all of these were turned on too. Yeah, I'm sure. I didn't print all of these. I didn't print every single one, but I'm sure some of them are not available on some systems. But this is the kind of thing you do, and you look at these characteristics and you look and see what kind of device it is in order to get your your code to adapt. Okay, this is also where you find out about the memory types. Memory types belong to the physical device. And so this is where you're finding out about which memory banks are device local, which are host visible. And this is the kind of thing I had gotten myself. Here's where you find out about the family properties of a physical device. The Q families belong to the physical device. And so you're asking the physical device about the Q family properties. Here's what I had gotten. And notice there's a lot of Qs in family 0. That's because you potentially have a lot of graphics command buffers being filled at the same time by multiple threads and are going to get submitted to different queues. So again, you can look at this, you can print it out, you can make your program adapt. So that's physical devices. Logical devices are sort of a mapping. That is, most of the code you see in the Vulcan code, the name of the logical device variable, is the first argument. So really, you are doing most of your Vulcan talking to the logical device, which is then front-ending an interface into the physical device. So it works like that. One of the interesting things that happens at the logical device level is layers. And this is something that I think is very cool about Vulcan and LunarG. LunarG is a company that's done just a horrendous amount of work in making Vulcan work and producing the SDK that we're probably all using or will be using. But think of it this way, is your program is right here. Vulcan is right there. And normally your program would be sending out commands, byte commands into Vulcan. But what if I could inject a layer in between here that intercepts those commands and then passes them on to Vulcan? But before it passes them on to Vulcan, it does something with them. That's what layers are. You don't want these layers in here for your production code, but there are a lot of interesting layers you can put in here that will do certain checks for you. And so, you know, these are the ones I like, but these others will work. Yeah, and so that's what layers are about. And you can actually have more than one layer in there. And so this is something you set up for whatever you're doing right now in Vulcan. But a lot of these layers, and there's new ones all the time, is you should go out to the LunarG website and see what new layers, because they're constantly adding new ones, which is great. And so this is a way of maybe printing out error messages if it thinks that you called a certain function the wrong way, or maybe just echoing all the arguments to a function so you can look and see what arguments are flying by in your Vulcan executable. The other thing is, this is where extensions get looked at. And these are the extensions that I wanted to see. Okay, they're the extensions, and what you do is you go ask, is this extension around? Is this extension around? These are the two right here that we needed to run Glfw. And so this is the part of your program where you think about the layers you want and where the extensions are. And here's where you find out about the extension count. You make a list of the extensions, then you go get them. And now you can either print them out or you can test them against what you're looking for. You can also do the same thing with the device layers that are available. And so on the system I was on, these are the ones that it found. And again, the sample code, if you run it, will print this out for you. And it's great. Here's where I was setting up the queue. And this is part of the process for creating the logical device. Okay, so the queue create information all went here, but that ended up as part of creating the logical device. And notice the other things in here. Here's where the layers go. Okay, which layers do you want to see? Here's where the extensions go. Which extensions do you want to see? And so this is set up in the logical device. And notice if you wanted to, you could have other logical devices that all pointed into the same physical device. And the reason you might want to do that is you might want to have a logical device where certain layers are enabled and another logical device where different layers are enabled, but they both point back to the same physical device. So you're going to get the same rendering characteristics, but you're going to get different characteristics based on the layers. The reason I could think of doing that, although I've never tried it, is if there's one part of your code that you're having trouble getting to work correctly. So what you might want to do is have one logical device that you use for all the code up until that point that does no checking. Then from then on, you use the logical device that does a ton of checking. And then after you're through the troublesome part of the code, you go back to the quiet, the no layer logical device. I can think of doing that because then you don't get a ton of messages from code that you're already happy with. So anyway, this is how you set it all up, and it's cool. Yeah, you can get the queue as well. So that is it for today. Again, that's a lot of work to get through this, and I appreciate you hanging out through this whole thing. I'm assuming you're still here. I'm hoping you're still here, but you have a lot of resources. If you go to that website, this website, you can get these notes, you can get sample code, you can get a zip file that's got the whole built solution for Visual Studio. You can see the individual notes if you don't want to look through a big note set. And again, Vulkan is very cool. It's going to evolve a lot in the next few years, and it's cool that you want to be part of that. Thanks a lot.